Okay, then we have some specific properties of this distance measure, which is sometimes important, sometimes not. More from a mathematical and a theoretical point of view. Very often it's not really a big deal in terms of the application, but we will come to the point later, or just in a minute. So if the distance measure is a distance function, it has three very specific properties. It's reflexive, non-negative, and symmetric. So you probably know that already from KDD1. A distance function, so a function, a mathematical function, is usually reflexive, non-negative, and symmetric. And if a function is in addition, it satisfies in addition the triangle inequality, this distance function is also a metric. Yeah? And very often algorithms claim that they only work with metric distance functions, and in many papers and many comments you see that we came up here with a distance measure, but it's not a metric. Is that a problem or not? Well, very often it doesn't really matter, even for the methods that claim to work only with metric distance functions. But metric distance functions, or metrics per se, have some very nice properties in terms of mathematical properties, which can be used especially for performance reasons. So just for the patterns themselves, you typically don't need metric distance functions. Yeah? So just because the algorithm works with a metric very often means that it uses metric properties for performance reasons and not for accuracy reasons. Yeah? So sometimes there's much ado about distance functions that are metric or not metric. Don't take that too serious or too hot cooked. Yeah. Okay, some comments here. Sound mathematical interpretation of matrices, of course, of matrices, of a matrix. The nice thing with the feature transformations is that domain experts can model their notion of dissimilarity or similarity. Metric distances also allow to tune efficiency. That's what I just explained. Metric properties are mostly about efficiency and not about accuracy. There is a long-lasting discussion of whether the distance properties, and in particular the metric properties, really reflect the dissimilarity we as a human perceive. So here is the potentially contradicting example that a metric is really what we also perceive as humans. So we as humans are non-metric beings, I would say. So and why is that? Here's the contradiction of the other claims. So we have a candle and a ball. So they have no properties alike, and so the similarity should be smaller than the similarity of a candle and a moon and a plus a moon and a ball. Yeah, that would be the triangle inequality. And as you see here, those two pictures are quite similar in terms of the lumen. Yeah. The light, so we have a lot of dark colors in there, so they might be the pictures might be not the objects on the pictures, but the pictures themselves will be quite similar in terms of luminosity. Yeah, and those two pictures will be quite similar in terms of the object, which is a round object on the picture, whereas those two pictures don't have any properties shared. So the similarity of the distance between these two objects is probably larger. The distance is larger than this distance plus this distance, which is a contradiction to the triangle inequality. Yeah? So the triangle inequality says that this is a smaller or equal, but in this example it's not a smaller or equal, so the right hand side is probably smaller than the left hand side of this inequality. Yeah? So, and that is probably a good counterexample why we as humans are not, at least not always, metric beings, so to say, yeah, have a metric perception. Okay, so another point is we talked about similarity, dissimilarity distances, and I somehow told you that similarity is something like the inverse of distances or dissimilarity, which is somehow true, at least in an abstract way, but sometimes it's not so easy to just convert the one into the other. Yeah, so typically most data mining methods work with a distance measure, but very often for the domain expert it's much easier to come up with a similarity function. So how to somehow convert those two things into the other. So is there a transformation from similarity measure into dissimilarity measure? Well, any monotonical decreasing function can do the job here, but you have to take care, because the similarity function or similarity measure goes from 0, which means totally unsimilar, to some maximum value, which means, but what is completely similar is identically would mean infinity, similarity of infinity or whatever, and the dissimilarity is the other way around. So 0 means distance of 0 means it's identical, and if they are completely not similar, then the distance is very high. Yeah? And how to convert these two measures with completely different semantics is not so easy. So typically you apply some function here to smooth the distance or the similarity, whatever. Yeah. So here is the equality from similarity to dissimilarity. And there are some prominent similarity functions that can be used, for example, exponential, logarithmic, or linear. You see they have different meanings or different impact on how to transform that. So here is the delta is the dissimilarity value, and the similarity value is on the y-axis. And you see they have different, of course, different impact, those different similarity functions or transform functions. Yeah. So the key message here is if your domain experts came up with a similarity measure, that's fine, but your method probably need a distance function you want to apply to that data. So transforming the similarity measure into a distance function can be quite tricky, and has to be done very carefully. Yeah. So just keep that in mind, so that you're not getting some surprising results. Yeah, here are some similarity measures that are quite common. So the dot product for two vectors, d-dimensional, high-dimensional vectors, is a similarity measure. Yeah, the cosine similarity measure, which is the angle, the cosine of the angle between the two vectors, is also a similarity measure. And the Pearson correlation, for example, is also a similarity measure. Yeah. Random walk kernel for graphs, for example, which counts the common walks, random walks in two graphs, is also a similarity measure. So they measure the similarity, not the distance. Yeah, take care about that. The other way around, distances, some examples here. Of course, you know the Minkowski metric, so the LP norms already, which is this formula here. You take the column, the feature-wise differences to the power of p, sum them up, and take the pth root of this here. Yeah, and you can use any p here. Actually, you can also use a p smaller than 1, which is the so-called, or which results in so-called fractional Minkowski distances. Then for p equals to 1, you know it's the Manhattan distance. Yeah, think about the Manhattan thing that you would just go blockwise. So you just sum up each individual feature-wise distance. P equals to 2 is the Euclidean distance, and sometimes also people use this maximum distance, P equals to infinity, which just takes the maximum of the feature-wise distances. Yeah, so the maximum feature distance, this should read as x I, of course, here, and yi. Yeah, sorry for that. So this is a very common thing. Mahler-Nobis distance, which is more or less the LP norm plus similarity matrix, is of course also a distance measure. Hamming distance for categorical features, where you just count the number of disagreements in each feature, is also of course a distance measure. Yeah? So once again, please take care about the difference between similarity measures and distance measures. Yeah, that's all for this one, and the next podcast will be on section 2, challenges.